Good morning. I'm Daryl Brugink, Executive Editor with No-Till Farmer, and I'd like to welcome you to this morning's webinar where we're going to look into the relevance of soil biology to your no-till operation and more specifically, how you might be able to achieve a better assessment of both your soil's fertility levels and soil health. Today's No-Till Farmer webinar is sponsored by Woods End Labs. They are the developer of the Solvita CO2 soil test, and we want to thank Woods End Lab for making today's webinar possible. And we also want to thank our presenter, Will Brinton, the inventor of the Solvita CO2 soil test, for leading today's webinar. So with that said, we want to thank you again for joining us, and we're going to turn over the controls to Will Brinton, who is joining us from Mount Vernon, Maine. Good morning, Will. How are you today?
Good morning, Daryl, and thank you for this opportunity to present.
You bet. You're coming over loud and clear. You sound great.
I understand several people in the Midwest are buried under snow right now, so I hope that hasn't negatively affected the attendance. Anyway, the topic today is the relevance of soil biology in assessing fertility and soil health. As you've heard from the introduction, this is Will Brinton speaking, and I operate the Woods End Soil Testing Lab, which I have done so continuously since the early 1980s. We also have a small research farm where I experiment with soil testing and cover crop and green manuring schemes, which has been a topic of interest for me for quite a period of time. I want to start today by concerning myself with the potential necessity of including soil biological parameters in routine soil testing. Now, you're all very familiar with soil testing, and many of you get reports like this with a focus on a few essential ingredients that go into yield assessments. The question before us today is, what about soil life? Is soil biology relevant in soil testing, and how can we incorporate it into it? Last year, I conducted a survey of 15 commercial soil laboratories in this country, and we found that less than half of them consider nitrogen testing in their recommendations, and 2/3 of them have never performed any kind of nitrogen mineralization procedures. So we know that this is a big challenge in this discussion. We stand at an interesting junction in time right now. In this chart here, we can look back to the astonishing yield growth as represented particularly in corn in the last 60 years. If you take this period of time before the yield growth, what is important about it, and I will discuss it later, is this area of yield increment, which is the biological underpinning that we are talking about. It turns out that farmers, before the advent of fertilizers and advanced breeding, were taking advantage of, although in a depletionary way, of soil biology because yields never went to zero. They stabilized and were sustainable at low levels because they were working on and burning up the biology potential in the soil. What we are trying to discuss today is how can we harness that and grow it in its own way upwards. We have applauded ourselves frequently for these astounding yield gains, but there are some emerging concerns. This is a recent published paper that broke down yield trends worldwide in major growing regions and major foodstuffs. Some disturbing indications are seen. One is that yields are stagnating, whether you look at Europe, Asia, or America in certain key categories. Again, this is depending on region and where the studies are done. But there's a considerable amount of data indicating this astonishing yield growth era is coming to an end. Even more concerning is what we already know. There's a considerable amount of yields that have never been improved in major categories of the world and in major crop categories. In other words, farmers are caught between crops that have had little yield growth improvement, those that have had astounding. Meanwhile, the costs of farming are rising. The study also looked at two other factors that I don't show here. One showed that in some areas of the world, yields continue to grow, and that's a sign of hope and shows where a lot of development needs to be focused. But the other graph was the most concerning, showing evidence of yield collapse in all the major regions of the world. In the study, they cited a variety of factors, contributing to yield stagnation. A common one was climate change stress. Mentioned also are salinization, soil erosion. These are all common themes. Pest and disease buildup. And then very importantly, we have here the depletion of soil fertility. So these are one of the areas that I want to focus on very particularly. If soil fertility is just an issue of nutrient management, then perhaps the future is very simple. More and better applications and more careful technology. But if we are dealing with biological factors as strong interactions, then these bets are not as certain. You've all seen the theory of collapse based on the three-legged stool model. If you knock out the biological underpinnings, you have an immediate collapse. This theory also holds for any other of the parameters. If you knock out the chemical or the physical by abuse of the soil, you'll have the same system collapse. It seems foolish to tempt fate and to pull any one of these legs off. The question today is how strong and important is biology being more seriously incorporated into fertility testing? Well, it's more complicated than a three-legged stool, and complexity, which is evident in nature, adds significantly to stability. You could easily say, if you look at agriculture, we've got 5 legs. I read a recent report that said it's really 6. There's 6 great secrets of success in cropping. If we have this kind of situation, you can afford to ignore 1 and maybe 2. You can abuse the soil structure and ignore the biology. Your stool is still standing. And I'm pointing to this to indicate one of the reasons I believe we don't notice some of the emerging instabilities or the issues with depletion of biology is that the system is basically very robust with all the legs it's standing on. Not only this, we have so many individuals, farmers, and agricultural companies working on individual aspects of agricultural stability such that the likelihood of any real collapse seems remote. In fact, what I observe among growers and agricultural professionals is a fair degree of confidence in our system. But this fact suggests that we should not continue to ignore other factors, such as the biology, simply because it's not evident now. How do we recognize these important and concealed factors and learn what their breaking point is and then design ways to work with it? I want to go right to the biological underpinnings, since I've mentioned that already. This is a graph that Dr. Rick Haney and I put together a few years ago for a presentation at the New Zealand International Soil Testing Conference. And what we did was we took the control plot yields of corn across Central and Southeastern America and plotted them against respiration or soil biology in the soil. These are unfertilized corn plots. In other words, researchers include control plots as a calibration of the effects of the treatments that they desire. Notice that in some areas of the country you have that 40 bushel yield potential without any nitrogen, and in other areas of the country we were up at 90 without any nitrogen. These correlate here on this scale with the biology because the organic matter turnover in the microorganisms are furnishing this yield growth. So yields can be increased above this line clearly based on additional fertilizer, nutrients, and other factors. But the fact remains that nature is working for you under the scenes, and the biological underpinnings are easy to be revealed when you do these control plot evaluations. So what's holding us back from looking more closely at this? I want to show here the basic chart that explains the area and the arena of our discussion. If you start on this side with the organic matter in the soil and break it down, you have the humus component, you have the plant roots component, and you have soil organisms. Soil organisms may be about 5% of the actual organic matter, and that group on this side breaks out to algae, fungi, bacteria, actinomycetes, and soil animals, all of which contribute to the overall performance and the respiration cycle of the soil. If you look at this, this slice is relatively small, 5%. And considering how low soil carbon is anymore in modern farming soils, we're talking about 5% or perhaps 2%, which is a very small number. That might suggest that you can ignore it, but in fact you can't. The way I like to describe this, and the way we present this, is all these soil biological interacting cycles. And I want to show how important and practical these are as we discuss the whole arrangement of these parameters. Beginning with soil organic matter, you have the crop residues, you have the root residues, you have manures, and any living detritus in the system, the accumulated humus in the system on which the microbes are feeding continually. There is no such thing as a dead soil, and I have rarely ever observed a soil that had no CO2 release. But CO2 release is itself only an indicator of two key factors that we'll address throughout. Here, the supply of nutrients, and here, the assimilation of CO2 by plants, which is an area that's very fascinating and has been long overlooked. This element of CO2 being an expression of the total microbial activity has been known since early in the 20th century and has been a guiding force in biological soil research during this whole period of time. So let's take a look at the big picture here. If you study soil biological factors, you begin to see that the simple nutrient theory that we have operated on is vastly oversimplified in a fashion, unfortunately, that implicitly ignores biology. Let's look at what's happening in the soil system. Soil biological transactions involving metabolism and CO2 release are furnishing soil animals with food. Guess what? They're also sequestering CO2, a topic of great interest these days among climatologists. The same cycle is meeting the plant needs for carbon dioxide, which I will discuss a little bit more in a moment. The same cycle is releasing available nitrogen and phosphorus to plants because the nitrogen and phosphorus is part of the organic matter compounds that are being decomposed in the soil. Finally, even more interesting is that the CO2 builds up in soil and acts as a natural solution or a solvent, pulling minerals out of the soil, which explains how nutrients are continually released from some of the mineral structure. One of the astonishing things to realize here is that nature is balancing several equations simultaneously. And what we are trying to do in studying the system and looking at it biologically rather than only chemically is to find ways to harness this and build it and improve our soil in the future. So I want to present here an astonishing fact based on work that I've been doing recently. The level of carbon dioxide in your living soil and how it relates to the overall cycle. It is not easy to perform these kinds of tests, and so few people are discussing it. We are trying to move closer and closer to simple field tools to make this visible. If you take a look at this diagram here, if you go down into the soil here and measure the soil atmosphere, the content of air in the interstitial pores, you will have levels as high as 4,000 parts per million of CO2. As you work your way upwards, the CO2 is in a way dribbling out of the soil and moving upwards. In the lower plant canopy and on the litter layer, we have levels as high as 1,500. Again, contrast this 4,000 here with atmospheric levels, which are about 400 parts per million. The astonishing fact here is soil biology is permeating the system with carbon dioxide. And there's a number of important things, as I've indicated just previously, that's going on. Researchers are looking at CO2 enrichment for plants. Environmentalists are stressing over CO2 levels in the atmosphere, but this cycle is one of nature's most basic functions. So let's put it differently. I'd like to point out here the crops are very hungry for CO2. Now let's give this a thought here and consider how it's related to biological fertility. I recently recalculated some of these CO2 figures that I found in early Swedish and Rutgers trials that date back to the 1930s, where they were measuring how much CO2 crops need and equating it to where it's all coming from. It turns out wheat at full growth has to utilize 10 cubic acres of air to get the CO2 that it needs. At full growth, the plant is absorbing 110 pounds of CO2 per day per acre. Corn is even more astonishing. 38 cubic acres of air would have to be filtered to supply that crop with enough CO2, which can be as much as 410 pounds of CO2 per day. There's emerging evidence now that crops could become CO2 limited, and this becomes a very important figure in looking at how this cycle here between the soil and the crops can be improved to furnish plants. Incidentally, if you take this 38 cubic acres of necessary air and measure it upwards, that's a mile and a half of air over the acre that would be needed. So one of the basic facts that I came across that we've all known for a long time that we've overlooked is that the life of the soil is really feeding plants carbon through the photosynthetic process. And I think that that is something that's worthy of looking further at. Here's a little sketch I did of the three forms of respiration that we're talking about in the soil. We have number one, the cycle, which many call the soil biological food web. It's consuming soil organic matter, it requires oxygen, and it produces carbon dioxide. The second cycle is plant root metabolism. This is the opposite form of metabolism since it requires oxygen and produces CO2 compared to the tops of the plants, which comprise the third form of respiration, photosynthesis absorbing CO2 and producing oxygen. A recent study of the metabolism cycle in an Amazonian rainforest showed that the entire cycle, all the CO2 and O2 produced by the system, stay in the system and never escape it. This is an astonishing fact about nature's cycle. The oxygen and carbon dioxide are in the topsoil, they are being produced by the plants, they are being consumed by the plants, and they're providing the plants with a nutrient cycle, hence the high productivity of some of these forest systems. The corollary to system health is obvious. Let's take a closer look at this with some real work that I've done in soil investigation. This picture I took last year at Phaeopody Farms in Pennsylvania provides some stunning evidence of the interaction of worms and roots, and you almost could say, which came first? Does it matter? Charles Darwin first alerted us back in 1880 to the huge significance of earthworms in agricultural soils. We are dealing here with a multitude of functions. Worms and roots are transporting organic matter and providing these aeration channels down into the soil. These earthworm canals are being studied by soil microbiologists and found to be highly enriched with carbon, which you can see if you look at the surface of the canals. They are high in nitrate, and the available phosphate is astoundingly higher than in the surrounding soil. The other thing that we have found is that worms stimulate other fauna in the soil, and they significantly increase CO2 respiration in general, not just because of the presence of their own metabolism, but the interactive and synergistic effects with soil organisms. Worldwide in farming, there has been a stunning decline in invertebrate populations in soil, and we just don't know what the unknown long-term effects of this will be. I did research early in my career on equating different tests to observed factors in the field. And here's a study we did from 17-year field plot studies where we measured earthworm canals in the soil and correlated it with two different ways of measuring respiration. The 24-hour test, which has now evolved into the CO2 burst test today, and a 7-day test, which was considered basal respiration. What we found was an astonishing correlation of soil respiration and the level of earthworms as indicated by the number of canals we could count in soil profiles. What we are seeing here is that if you can take a sample out of the field into the laboratory, dry it, grind it, prep it, and run a laboratory respiration test, it will correlate with field observations in a really significant way. This emboldened me a long time ago to start pursuing more carefully and diligently ways of bringing biology testing into the laboratory in order to gain greater indicators of what we were observing happening in the field. So over the years, these are all the methods I've worked with, accumulated in my laboratory, and experimented with. I would say there's a multitude of excellent but highly impractical CO2 methods for soil investigations. Some of the methods that are available today that are still used go back to technology as early as 1860s when manometric approaches were developed for soil studies. The early CO2 work that was done in Germany and Sweden that I read about used all these early very precise but time-consuming methods. Today we have advanced gas chromatography, we have infrared systems and so on, but the overriding problem here was when I was offering this as part of soil testing, I had to charge $75 just to do this kind of work per sample, and I realized at a certain point in the early 90s there would be no way to expand the biological discussion into the soil arena if we couldn't make practical testing. This explains why I moved into inventing a new way of doing the test to make it feasible to do cost effectively. Our goal has been to scale the biology of soil testing for a modern laboratory. We are presently now working with dozens of soil labs in the USA and overseas and are committed to a methodological improvement. You are all familiar with soils going into the laboratories here in sample bags, and things move through a lab in a fairly automated way, and laboratories have to have the ability to handle a large volume of samples in a reasonably short period of time. We devised the test so that a significant amount of samples could be done during the day, and we use simple laboratory incubators as indicated here to control the temperature so that laboratory A, laboratory B, and C around the country are getting similar results. We've worked with proficiency programs and are really proud that the results reported by laboratories are improving steadily. We've developed a technology process that standardizes the chemistry so that the test is the same every time. Growers and crop advisors are the other half of this equation now. You need to be aware that the technology is now available to make soil biological testing an affordable reality. The CO2 burst procedure that is known today in many laboratories has gone through several stages of development. And the first was work I did with John Duran in Nebraska in developing a field test, which you can still find on the USDA website under the Soil Quality Institute arena. In 2005, I started research with USDA ARS after meeting Dr. Rick Haney at an international soil testing conference. We both shared the same interest in respiration. We had both spent at least the prior decade working with it, and we had both reached the conclusion that the discussion of soil biology wasn't going to go beyond the research lab unless we could devise a procedure to make it more practical. So the basic invention of my Solvita chemistry to capture CO2 was modified into what we call the CO2 burst procedure. It also means it's a drying rewetting test based on a well-known and long-forgotten discovery in the 50s in Kenya and in Germany that when you allow soils to dry down here and then moisten them, you get a significant little burst of CO2 right here. If you don't let the soil dry enough and re-moisten it, you don't get the CO2. So we have standardized the method here so that laboratories are measuring this peak here very accurately, and it's a significant indicator of the biomass of the soil and its biological potential. Another thing we had to do was realize and recognize all the existing soil laboratories and the enormous amount of work they do in serving farmers around the country. Now this is a live map that you can access on our own website so that you can go into your region and investigate what lab might be available, and you can talk to them and find out what level of biology testing. There are also other labs that are highlighted that have moved into the soil health tool arena on this map that you can zero in on and discover. By building this test into a large successful network of commercial soil laboratories that are already in the business of serving farmers. We believe that we can see the soil biology movement take root in a normal structure of innovation in the private sector and agriculture. We hope you believe this too. It would be very helpful for anyone who believes soil biology testing is not available to pick up the phone and call a soil lab and discuss it with them. There are many more labs in the country than indicated on this map and around the world that still do not offer any testing comparable to this. I want to be practical here and look at what the results look like when you measure respiration. Here are 8 soil samples that were sent to our laboratory which had interesting and different histories. Several of them were from the southeast, and one of them was a virgin prairie soil from Nebraska, which is here on this side. An intensely cultivated truck farm soil from South Carolina had one of the lowest respirations that I've ever seen. We've seen values under 10, but on a daily basis, 10 parts per million CO2 indicates an extremely depleted soil. In contrast, we looked at a couple no-till soils very close to this soil in the area, for example, here, with very healthy respiration rates. This soil had respiration in the subsoil, which was still twice the respiration rate of bare-tilled tobacco soil nearby that was receiving no cover cropping and had a lot of tillage involved. We came over here and examined some cover crop soils, and one of the highest results here was a multi-species cover crop that had been this way for about 5 years. Topping the scale, as you might expect, was the virgin prairie soil. It was 78 parts per million. We have seen soils higher than this. A level of this magnitude indicates a soil that has built up a reserve of humus and microbial activity that's quite substantial. This particular soil I will be pursuing more in the future and reporting on it because it's gone into no-till farming recently, and we're going to monitor where the changes go. I have more recently introduced another form of test because I am very concerned with looking at what I call upstream pools of organic nitrogen. A recent study published out of Illinois correlating the use of nitrogen fertilizer with reserves of total nitrogen in the soil has provided stunning evidence of a continuing decline of organic nitrogen in soil despite these nitrogen inputs. What this tells us is that nitrogen fertilizers are not getting into the organic fraction of soil. In fact, there's evidence of a priming effect in speeding the decay of soil organic matter and causing net depletion. One of the important things is we have to develop tests that reveal this. Now, this particular test, which I called SLAN for labile amino humic nitrogen test, is those same 8 soils, and the stronger green the color, the more organic nitrogen is bound into the humus fraction. Now, this is particularly startling if you look at these soils. Once again, here's this continuously tilled truck farm soil with a very, very, very low level, indicating a completely biologically depleted state in that soil. Ray Steyer has been written up in No-Till magazine before, and is a no-till farmer of at least 30 years, and he had the highest level of organic nitrogen in the soil. Incidentally, he is using no inorganic nitrogen anymore to get above average yields of silage corn in his farming system. His subsoil was enriched with humic nitrogen. If we go over here to the virgin prairie, we see it had a natural reserve, not as high as the no-till soil, but it's astonishing if you think that a no-till farmer has taken a soil and made it even higher in organic nitrogen than the virgin prairie. Now again, these are different soil types and regions, so you have to allow that part of the difference would be explained by that. But what we are trying to do here is create both a visual and a quantitative way to begin to look at these upstream pools, because you can use it to tell yourself if your management practices are building the soil or depleting it. The laboratories are able to quantify this method and give you an actual parts per million or pound per acre readout. Nobody knows yet how much of this is available. We have not given any indications exactly what is available, but we are seeing a clear indication that this could be a pass-fail test for corn nitrogen responsiveness or not, because we're correlating those levels with farms that are successfully reducing nitrogen inputs. Let's take a further look at this issue of organic nitrogen in soil. I would recommend to everybody to go down and visit the Alabama Ag Experiment Station old rotation plots. This is one of the oldest cotton studies in the world that was set up in 1896, examining the effects on long-term cropping of the use or non-use of cover crops. In this particular example, this poor crop of cotton here, which had been fertilized, had no prior winter legume, and here's the same crop here with winter legumes sown every fall and then tilled under in the spring. The significant difference in these yields and the appearance and health of the plant has to do with soil organic nitrogen. It has been accumulating because of the winter legumes. Sadly, many of these studies that are showing a decline in soil organic nitrogen suggest that nitrogen inputs, if they are not correlated with cover cropping and roots development, will not add to the lasting humus nitrogen pool of the soil. Had we had available earlier in the century test methods for reserve pools of nitrogen, instead of only focusing on soluble forms, I believe we could have made significant advances and would have not seen some of these declines. This all goes to my point that unless we stimulate a mild revolution in the soil testing industry as well, we will not be able to accomplish all these goals. As part of our commitment to growers, we have also made available a simplified form of the original field basal test that I mentioned that I first worked on with John Duran in Nebraska. This enables you to actually take samples that are relatively undisturbed from the field. It's the same 24-hour setup, but what we have done differently now is we've simplified it to a different kind of quantitation, which is the pounds per acre of CO2 that is being released from your soil. You can now experiment with how location, crop, soil depths, and so on are influencing the level of life in your soil. Basal respiration tests conducted in this way do not give as high an indication as CO2 burst in the manner that we have standardized it in laboratories, so you ought to consider doing both if you're interested in this. The field results show you daily reality, and which is changeable. Temperature has a significant effect. Moisture has a significant effect. But it becomes very interesting and fun to monitor some of your crops in a more immediate fashion. I want to discuss a little bit reporting results. When you deal with biological testing, there is no one single way to take a result such as our CO2 respiration or SLAN and say it indicates this. Some of the laboratories we're working with are simply using it as an index of soil biological activity. University of Maine Soil Testing Laboratory is an example of that. It's become a very popular test because people want some kind of indicator of how their soils are doing. Growers may wish to use it just to monitor soil improvements without using it in any predictive way. We can at least say we know it correlates with soil biomass, which is the microbial infrastructure of soil, and therefore you can start monitoring the biology of your changes. We have seen many farmers use our tests and compare it with strip plot results where they withhold nitrogen or other nutrients based on what the test is indicating. We've got some stunning results this last year from many farmers who have found that they can maintain excellent yields with less nutrients if the biological indicators are positive. Over here I have a picture of Ray Steyer standing in his corn. This corn has received no inorganic nitrogen. His only use is manure at about a rate of 4 to 5 tons an acre every other year. So there are some nitrogen inputs, but his soil biology indicator based on our tests are very excellent. So we know that he's achieved a sustainable system. Another thing is just to work with field level CO2 output. We're going to see a lot more interest in this in coming years as we start focusing on whether crop physiology can be improved by better soil biology, in the sense that photosynthesis will not be CO2 limited. A lot of work has to be done in this area. Obviously, our tests integrate into soil health tests, and I will show you some examples of that. In other words, laboratories doing common nutrient testing can add to it these cost-effective, simple tests and find ways to report it to their customers. Obviously, a big goal here, or the holy grail, is to indicate potential nitrogen mineralization. And many people think that we release the test purely to do that. It's very important to understand that nitrogen mineralization, though a given and virtually lawful relationship of CO2 respiration, does depend on other factors in the soil, in particular the carbon-nitrogen ratio. If you're working with high carbon systems with lots of crop residues, which you should be, you are also immobilizing nitrogen at the same time that the increased level of microbes are mineralizing it. That's why you'll see, and if you've done a soil health tool test, as we have worked on developing with Rick Haney, there's an additional CN ratio test in that procedure to help protect us from overestimating nitrogen mineralization. We certainly don't want to give soil biology a bad name by making overly optimistic projections of what you can expect in soil testing. Finally, working with SLAN, we're getting more and more evidence, almost in the way that the ISNT test was developed, to indicate the difference between responsive and non-responsive soils when it comes to nitrogen. We think this test, laid on top of soil biology tests and your common spectrum of soil nutrient tests, can provide some really excellent indication on how stable your yields are and what you might have to do to improve the soil biology. I want to talk here about some of the examples of interpretation. Many of the laboratories we work with, both here and overseas, we've encouraged them to innovate their own innovations based on observed field plot studies and working with growers. People are doing their own calibrations. But if you break the soil down into a low biology class versus a high biology class, you can certainly see some dramatic differences. We have determined that the range of amino nitrogen by this test can go from 80 to 160. We're seeing levels as high as 300 to 400 in really vital, high biologically fertile soils. But it's a fairly narrow range that seems to tell us a lot about the potential soil to pack away organic nitrogen. The span of soil CO2 respiration is even greater. And again, anybody doing respiration has to distinguish whether it's done in a standardized lab setting called CO2 burst, or you're doing another kind of test that would be either a field soil type respiration test or a basal respiration. These results are different, and in our new system we're just giving you the pounds an acre of CO2 because we think that's a very important indicator that's different than trying to quantitate it at the parts per million level in the laboratory. What are the uses of these results? Well, very low biologically active soils are definitely indicative of exhaustion, soil exhaustion. Is there an exact cutoff? No. It depends on the region of the country that you're farming in. We in the Northeast here, where I farm, are blessed with high organic matter soils. Nobody's trying to get more carbon into their soils up here, but our soils tend to be cooler. The pH is lower and the biological turnover cycles are smaller. We do not have as high respiration per unit of carbon here as I observe elsewhere in the country in warmer areas. And that's a very important ecological factor that must be connected in with your evaluation of soil fertility and productivity. Where we see very high results, it suggests clearly the reduced need for nitrogen and possibly other fertilizers. This is one of the most important emerging areas, I believe, in this country, is there's continued evidence of over-fertilization with nitrogen. New models that I've been reading that have been published from economic studies indicate farmers see nitrogen as a risk tool and will use more to avoid risk, even though the use of it reduces their profitability. So there's an exchange going on between a sense of risk and the cost of avoidance that is becoming an increasingly tight balancing line here as we go forward into the uncertain future of increased costs of implements and depletion of our soil reserves. I want to come back to the point about integration of our testing, the Solvita test, into other laboratory work. This procedure, these two procedures, the CO2 and the SLAN, the amino nitrogen test, can be integrated into any soil lab report. I'm just showing here two examples from two continents. On the left is our laboratory report, which is based on the USDA ARS soil health tool, integrating soil biological factors, giving you an indication of the relationship of different nitrogen species. On the right here is the soil lab check from the United Kingdom as offered by NRM Laboratories. In this system, they have got a microbial activity scale, and then they equate it to the nutrient balance and give you a soil health score that's similar to what we're doing in this country with the soil health tool. But the point is, these tests can be innovated, and laboratories and soil scientists working with their crop advisors and agronomists should be encouraged to experiment and explore ways of integrating these procedures. There is no limit here on what can be done, but the message is some of the pressure, some of the encouragement should come from the growers. You should feel as a grower that you have the right to call a laboratory and ask if they are doing some kind of soil biology testing that you can start to use to monitor your soils. Many of the laboratories tell me we don't yet know how to interpret it, but now we have several years of work behind us and a nexus, a whole network of laboratories that are recording results and comparing them. So we're learning very, very quickly how this system will work and how it can be integrated into soil nutrient testing. So I want to come back to the point that I started with at the beginning of this presentation. Obviously, nutrient-based yield theory has served us, we could say, served us well for 150 years. The problem with it is it was invented and developed without any concept of soil biology. Indeed, part of my graduate work was reading Liebig in the original German, and I noticed that he was insistent that there was no relationship of crop yields to soil biology in the sense of soil humus and organic matter cycles. In other words, a fundamental error in omission was incorporated into the very founding of soil chemical theory. So we stand at the present time in a situation where we really need to develop a biological corollary for nutrient yield models. And notice, in biology, you don't have a law of diminishing returns. It's almost the opposite. As the system gets better, it gets better in a number of very astounding ways. Across America, farmers, crop consultants, and soil labs are testing these new tools. Many laboratories are beginning to add a test here based on the work that we have done with them over a number of years. As we go forward now and as we have these new concerns about where will our yield stability come from, I'm proposing the overlooked arena is soil biology. I believe that it is a new frontier to stabilize yield growth. It's even possible we could see further yield growth, even though there's evidence of stagnation worldwide, if we just refocus on soil biology and help it because of all the things that it can do. Not just in a nutrient release cycle, but consider all the disease control aspects of microbes in the soil. Consider the CO2 that I told you about, that this active canopy of corn is hungry for. Consider that that could be coming out of the soil and be going into the plants right where they need it. These are some of the challenges ahead of us, and ways in which I would like to work with you are to get the crop advisors, farmers talking to their soil labs, and the universities and the government can play a very important role here by listening and watching what we're doing and asking how they can help. I've come to the end of my presentation here, and I want to thank you, but I want to do something else. I want to thank all the innovation that's going on as evidenced in these pictures here. These are photographs taken very recently at field days that I have participated in, offered by the No-Till Alliance of Pennsylvania. Look at some of the extraordinary innovations, for example, with equipment that we are seeing in handling and preparing cover crops for soils. When I grew up and studied agronomy, looking at a field like this on the right would be appalling. We would say, that's messy. There's something wrong with that. Are those weeds? What's all that litter doing there? The whole arena has changed with all the innovation in cover cropping that we are witnessing across America. I worked on cover cropping in the 80s. We called it green manuring back then. And one of the issues was first of all, it was considered only relevant to organic farming. And secondly, we talked always of plowing it in, tilling it into the soil. I am very grateful to all the growers and researchers who are showing that tillage can be removed from this, and in fact the gains to the soil system are even greater. For those of you that have attended this session, I encourage you to visit our website and particularly take a look at the soil map, which I have indicated here. It's interactive and you can locate labs in your area and talk to them. If your lab presently does not do this kind of testing, point out that a lab nearby may be doing it, because we are trying to inculcate soil biology testing into the free enterprise system in this country, which is where I believe it will really grow and take off if handled in the right way. Secondly, I want to emphasize, here's my email address. If you do have questions, please send them to me after this session, and we will try now in the time that remains to answer some of the questions that have been sent in. Darrell, I'll turn it back over to you momentarily to start this question and answer session.
You bet. Thank you, Will. Excellent topic here, particularly judging by the amount of interest and also judging by the amount of questions we've received. It is a very high interest topic. I know we're not going to get through all the questions today, but for all of you online, want you to know that we're going to get through as many as we can here live. Will's going to he's going to start by tackling some that were submitted already ahead of the webinar that he thinks would be appropriate to answer at this time. But any questions that we don't get to, we're going to kick those back over to Will, give him some time to write out some answers to those, and then we're going to make them available with the archived version of this webinar. We will be making it available to all of you via email. It'll also be being posted on our No-Till Farmer website. So that being said, Will, I'm going to turn it back over to you. If you want to kind of start by going through some of the questions that were submitted ahead of time that you'd like to answer at this time, let's do that. And if you get through that list and we've still got some time, let's go after some of these questions then that were submitted during the webinar.
Okay, great. I just threw up on the slide here a picture here that goes to the heart of the matter, and it makes me think of build the field and the players will come. The innovation that's going on in this country right now, right at the farm level, almost defies expectations. We're seeing growers making the calculation that they are in a race against time to maintain profitability while all the other costs of farming are rising around them, and working to mimic nature is where the next increment of yield stability will come from. Now, on the question list, here's an interesting question. Can this biology test be used to prove the amount of damage done to the soil by tillage? Well, yes, of course, but I like to say always, it's not always that simple. Recently, I've been working with Rick Kurzbergen here in Maine, an extension professor, and we're comparing different cropping systems. And last year, the no-till soils scored higher on a biological index, and this year, the cultivated soils did. Now, what you have to find out when you do these tests is what happened in between. I have often found cultivated soils have higher respiration because they had just turned into the soil liquid manure or or a large amount of solid manure that stimulates biology not just for a week, but all summer long. So you can have examples of biology appearing higher under cultivation if at the same time they've been mixing organic fertilizers into the soil. Another question came in: how does soil biology management change from northern to southern climates? I mentioned earlier in my presentation that we have a slow cycle here in the Northeast. We have a lot of accumulated organic matter, 6 to 8% in some of our soils. The cycles are very slow. As you go further south, if you have the moisture, you have high turnover cycles. In some areas, I've seen cover crops that are rolled. You can picture these cover crops here that have been rolled. They will disappear in a very short period of time as the next canopy of crops are growing because the temperature and the moisture are there to support it. As we go way further south, in the southeast, into Texas and into California, we are seeing some of the lowest organic matter levels ever compared to other parts of the country, but consider how fast the soil biology cycles there are. So you need more intense intercropping and cover cropping to maintain the organic matter in these warmer cycles. Now we had another question here: how does soil respiration change from March to September? Well, it depends how you measure it. If you send a sample to a laboratory and request this standardized CO2 burst test, you will not see much difference through the course of the year because we've calibrated it at a slightly above room temperature, around 75 Fahrenheit test. We've calibrated the moisture in the test. So we're trying to eliminate some of the background variables. But if you do basal testing in the field, you will find a distinct cycle that increases in the summer and then declines again in the fall. And this can be fun to track it if you do the testing yourself every few weeks. Another question: is there any correlation between CO2 emission levels and ratios and quantities of NPK? Well, no, not really. I'm seeing many soils that test very high in nutrients that have a low CO2 respiration. Well, they're depleted soils, but they're being well fertilized. On the other hand, I'm seeing soils that are high in nutrients and very high in respiration. These are soils that have been well fertilized in the past. They may have gone into no-till and cover cropping, which has enhanced the biology. And some of these fields, frankly, have been over-fertilized in the past, and we have very high levels of phosphorus, for example, and high levels of residual nitrate, but they're still functioning at a very high level of biology. Some of these systems, I say, we can put the brakes on and coast a little, and we're still going to get excellent yields without pumping in all the nutrients. One of the questions was, what happens to soil microbial activity with cultivation practices as compared to no-tillage practices? This is one of the most fascinating areas for me because the agronomy that I learned didn't include no-till in the early days. We were all cultivation farmers, and I had a specialty in biological and organic farming, and what we are struggling with now is trying to pull back on the tillage so that we're not doing as much disruption of the soil because we don't have available the herbicides to control the cover crops. You've seen a lot of innovation here, and we're seeing no-till farmers use less and less chemicals and less herbicides because the cover crops themselves are doing such natural weed control. So it's very exciting that we're seeing some of this convergence of these different methods. Do you have any evidence, says another question, of the increase of soil microbiology under no-till compared to conventional? Again, a similar question, but yes, there is clear evidence. I showed some slides earlier on Ray Steyer's farm. We're seeing outstanding levels of biology on this long-term no-till farm that does include intercropping of multi-species mixes as a soil building cycle with his silage corn. One person writes in, is there a best way to conveniently measure water infiltration? We find these tests we do correlate indirectly with water infiltration, but you really should measure water infiltration in the field with the field ring method. At several of the workshops in Pennsylvania this past year, we always have somebody like John Jabirka present from NRCS showing how easy it is to do water infiltration tests in the field. And there's going to be more and more literature out there showing that this test can be performed because it should correlate well with improvement in soil structure. Somebody has asked, what is the best time of year to test for nutrient values from the microbial point of view? Well, I think you have to sit down and come up with a sampling plan and then stick with it. I know many growers feel they have to run their soil tests in the fall, and we have found we get good indicators of biological activity. We see lower nutrient levels in the fall than if we do it in the spring because the soils actually are recharging somewhat over the winter. We don't see the microbial activity change over the winter. These microbial reserves are long-term. Microbes have learned to survive under extraordinarily variable circumstances and are not readily and easily impacted negatively by changes in the climate and the weather and so on. So pick a time of year that's convenient for you and start focusing in on it. I'm wondering if we have time for a few more questions, Darrell. What do you think?
We do, Will. I'm just going to go, I'm looking over the list that we've had submitted here this morning. Let me just start with this. When you're taking soil samples for this test, could you talk about the soil depth? Are you looking to go, where do you want to really take your samples, I guess? So.
Well, it's common in this country to do 0 to 6 inch sampling. If you're doing pasture soils, you should probably be sampling even shallower. If you're doing forest soils, and there have been some questions that come up about that, it's a very, very different scenario. One of the things that I like to do is encourage growers to take a subsoil sample as well. So in other words, you might do 0 to 6 and then 6 to 12. We know certainly in the Midwest they're doing deep soil nitrate testing. There would be no reason why we couldn't combine soil biology with that. I can tell you from long-term field plot studies that I have worked on in my career, there's significant evidence that as you improve soil biology, it moves downward into the profile. In other words, it's not just that you're enriching the topsoil, but the effects move downwards. If you remember the picture I showed earlier on, the roots are carrying these benefits down. The earthworm canals are carrying these benefits down. I have another picture here that I didn't show, but look at this. This is an earthworm profile that I did on a reconstructed soil profile on my farm here. This is a clover ryegrass mix. Which level of soil should we test here? We have the 0 to 6 zone here. We have the 6 to 12 and the 12 to 24. It's very clear if you look at this that the roots are cycling nutrients all the way down. And one thing I would have mentioned earlier, a recent study, a paper published by Professor Emeritus Bill Liebhardt called Moving Beyond the Soil Test points out roots are exploring up to 200 cubic feet of soil per plant, and yet our soil test models assume only 10 cubic feet. So let's expand our soil testing downwards. And again, as I said earlier, come up with a plan and do it consistently. Maybe 0 to 3, 3 to 6. Right there you'll see a stratification. But I would encourage people to do it in a uniform fashion.
I got Will, a couple questions here related to SLAN, and one of them is, I'll read them both to you, but how does SLAN correlate to the total nitrogen or your total organic matter? And a similar question would be, does the SLAN test really mean that the plant will uptake that organic nitrogen that you've got? Or, you know, if you could maybe talk a little bit more about SLAN in relation to those comments.
SLAN certainly correlates excuse me, with soil organic matter. In work that I've done with Rick Haney, we find it correlates very significantly with water extractable organic nitrogen. In other words, the water extractable organic nitrogen is coming off of the bigger pool of the humic amino nitrogen, which is part of an even bigger pool of total soil nitrogen in the soil. There are almost no laboratories anymore that will do a total N test on soil. Many of us are equipped to do it, but it's another cost factor. And the levels of total nitrogen in soil are extremely low, so you require a high level of precision to actually quantify it. That's different with SLEN, which is very easy to do, and we're measuring a smaller pool very accurately. So the relationship to organic matter is very clear, but we're seeing large differences in soils in terms of the amount of potentially available humic nitrogen that seems to be present. Daryl, was there a second part to that question?
Well, the question was here, does the SLAN test really mean the plant will uptake that organic nitrogen, perhaps depending on climate, whether you've got, temperature variations or excessive rainfall? I guess that was, I don't know if that makes sense to you or you can answer that. So
Yeah, absolutely. We're not saying necessarily that plants are taking up that organic nitrogen. We're saying it's part of a whole process of release and mineralization. So what was humic amino nitrogen one day, tomorrow actually could be nitrate, because the microbes are consuming the carbon and releasing the nitrogen. There are specific groups of in soil that take it from amino, amide, and protein form down to ammonia form and then down to nitrate. And if the soil becomes too wet, there's another group of organisms that move it sideways to nitrite. So regardless of exactly whether they're taking it up in organic form, and there is evidence plants do absorb organic soluble nitrogen, the point is that that SLAN will eventually become available. And we have collected this last year for the first time some stunning correlations of levels of humic nitrogen tested by SLAN and whether or not the corn crop was responding to nitrogen. And in a way, this all goes back and supports Mulvaney's original work in Illinois, showing that there are cutoff points using, when you do these total humic amino nitrogen tests, there seems to be a range that you can get into where the soil is so rich in organic nitrogen, you really could seriously question whether any additional nitrogen was required.
okay. We're going to do one more question here, and this one's kind of starts with a statement, so you might want to listen to this one, tell us if this is accurate first and foremost, the statement. But the individual says, I understand that Solvita measures microbial respiration and is a biological measurement, and that aggregate stability is a physical measurement. Have you looked at a correlation between high Solvita measurements and high aggregate stability measurements?
Absolutely. We routinely include in our soil testing microaggregate stability testing and have done so since the mid-'80s. So we've accumulated a considerable amount of data that shows a clear correlation. Keep in mind it's also indirect because it is substantially affected by soil texture. It may be more difficult to experience aggregation in sandy soils than in soils higher in clay content, so that you won't necessarily get direct linear correlations, but they have to be factored against the soil type. But keep in mind, if you will, the holistic picture I've tried to present here, that as you improve soil biology, the factors that you are fostering there are indirectly affecting soil structural integrity, increasing the aggregates function in the soil because that's a biological function, and that in turn increases the rooting depth and the root quality and the earthworm activity, all of which contribute to this macro aggregation down to the micro aggregation. So we should seek correlations between these, but we should not oversimplify them as simple linear relationships.
All right, real good. Will, thank you very much. As mentioned, we didn't get to all the questions, but we're going to capture those. We're going to share those back with Will to answer. And as soon as he's able to get to those, we're going to post those with the webinar replay. And so I want to thank Will again for leading today's presentation. I also want to thank Woods End Lab and Solvita for sponsoring it. And also thanks to my right-hand man here, Cole Vandermouse, who's helping us, guiding us through the technology of the webinar. Hope that you guys have been able to get your crops out of the field before this winter cold snap arrived, and that you had a great crop. And we look forward to having you join us for our next No-Till Farmer webinar. Goodbye for now.
Thank you very much.